Hi, everyone. Thank you for joining us today for the first of our three-part webinar series on fiber and RF basics, co-hosted by TRS-RenTelco and Viavi Solutions. My name is Lindsay Welch, and I am the marketing manager at TRS-RenTelco, as well as the moderator for today's event. A few housekeeping items before we begin. This webinar is being recorded. We will send the presentation slides, as well as a link to the video recording to all registrants later this week. We'll hold a Q&A at the end of the webinar to keep us running on time. Feel free to submit your questions as they come up using the questions section of your control panel located at the bottom of your screen. For those of you just joining, today's webinar will cover fiber optic technology basics. Dan from Viavi will present on behalf of Jeff Harmon, Viavi Senior Engineer. Unfortunately, Jeff was unable to make our call today due to the rolling power outages across Texas. Dan will provide an overview of fiber and connector types of impairments, and best practice for installing, certifying, and troubleshooting fiber optic systems. But before we turn things over to Dan, I'd like to introduce Michael Androli from TRS-RenTelco. Michael is TRS's Director of Sales and Operations for our Canada, Europe, Middle East, and Africa regions. Michael has worked in the test and measurement rental market for the past 25 years, all of which have been with TRS. He's been managing Canada's outside account managers and inside applications engineers for the past 21 years. Michael excels at helping customers optimize their equipment procurement strategy to ensure they get the equipment they need with the financial terms that best meet the circumstance. We know there are a lot of demands on your time, and we appreciate you joining us. I'll now turn the presentation over to Michael.
Thank you, Lindsay, and good morning, everyone. My name is Michael Androli with TRS-RenTelco, and for those who may not be familiar with TRS, we offer test equipment rentals, leases, and in-house financing for all of your test equipment needs. TRS is centrally located on the grounds of the DFW Airport in Dallas, Texas. We have a 120,000 square foot facility housing $500 million in test equipment and over 5,000 unique models. In our facility, we maintain a 20,000 square foot state-of-the-art calibration lab with over 30 OEM certified technicians, where we calibrate approximately 80% of our equipment right here in-house. Due to our location being on the grounds of the DFW airport, we can ship as late as 9 p.m. Central Time, allowing for next day delivery to meet your urgent needs. Here are a few reasons why it makes sense to choose TRS for your test equipment rental needs. First, we offer 24/7 customer care support, where you will always talk to a live person who will be providing you with any assistance you may require. We have a 99.72% quality rating, which means that almost 100% of the customers who use our rental services receive equipment that meets their needs and works right out of the box. We also have a very knowledgeable and experienced team of applications engineers who will help you with your equipment selection, your equipment configuration, pricing, and order shipment when you call us at TRS-RenTelco. With international offices and coverage in Canada, Mexico, India, Malaysia, and Taiwan, TRS can help you with your equipment needs no matter where your projects take you. And now, I would like to turn it over to Dan Smedja, domain sales expert for CIVT wireless metro fiber at Viavi Solutions. Take it away, Dan.
Thank you, Michael. Everyone, my name is Dan Smedja. I'm the guy with the hat on in this video. I work out of the house, so I think we all kind of figure out what that means. You wear a hat to conference calls first thing in the morning. So I work for Viavi Solutions. The CIVT product line, or CIVT, is an in-house acronym for carry around and virtual test. So we cover all the handheld products inside Viavi Solutions versus our network installed products. We're not going to be talking about those products today. Primarily the products that come in and out of TRS. I'm here to talk about the technology behind them. So this webinar is going to focus on fiber fundamentals, types of fiber out there. We're not going to go into fiber numbers, but we'll talk about the main classes between single mode, multi-mode, how they work in an OTDR and how an OTDR does its job, And then we'll focus in on fiber cleanliness and best practices around the #1 failure in any fiber network, whether it's wireless, data center, metro, cable, fiber to the home. There's a single fundamental point of failure that is roughly 80% of all failures. So we're going to focus heavily on that. As we jump into this, the Viavi Solutions page has ample training videos that myself work on, Jeff, my other 7 counterparts, on top of our daily activity of working with customers and helping with sales and technical support. We write a lot of quick cards. We do a lot of videos. So if you're the wireless side of the house, you may have seen my face or heard my voice on a lot of our YouTube channels. But these are our product offerings for help, right? So by all means, check out our YouTube video. You can click the like button. I still have no idea if that helps or not, but we always say it. So let's click the like button. The quick cards are pretty good. We update those every time there's a new firmware release. And of course, public webinars like this one, not this one per se, but public webinars we put out there for knowledge transfer. And as always, for those who have our tools, including TRS and all of you who may have the purple box, which is Viavi, all of our software updates are free. So the bottom is updatemyunit.net. If you go to that website, bookmark that. If you have any of our products from fiber inspection through OTDR, through OSAs, through our wireless products, and even our Metro 100 gig products, we don't charge for software upgrades. So by all means, keep your units up to date for bug fixes, future enhancements, all of that fun stuff. So let's talk about fiber basics. Fiber basics is good. It's pretty simple, right? There's 2 main classes of fiber on the market today. We have multi-mode fiber. And if you look at the picture at the bottom, multi-mode is a very large core. And then we have single mode fiber, which is the one on the right side of the page, which is a very small core. They have drastic differences in how they handle lights. Multi-mode, being that it has this humongous core in it, about 50 to 62 microns, is very cheap to make, and it works very well in short distances. For a lot of us out there, we've seen that as the orange fiber or maybe the teal fiber if you're working in data centers and legacy wireless networks. It's cheap to build because it is so big. You don't have to have a process that refines that core, that central glass, down very low. Allows us to send light with a cheaper LED type laser, which we won't really talk about, but in order to get to single mode, all of the components have to be upgraded to fit in that smaller core of single mode. So multi-mode is great. You're not going to see a lot of testing around it because, again, it's usually 4 feet to maybe 1 kilometer in length total, usually inter-office testing. So maybe you'll do an insertion loss test, but you're probably not going to stick an OTDR in there very often. We do sell them. They are rentable. They are out there. They're just not as prevalent as the single mode variant. So we look at single mode fiber. That core, that center white area of our picture is roughly 9 microns, right? To put that in perspective, a 9 micron core is about the 10th of the size of a human hair. And that would be on someone like my head, which is covered by the hat, right? I have pretty thin hair. So it's really small core, which is expensive to build, expensive to make. And now your SFPs or your lasers have to actually be lasers and not just LED diodes, right? So single mode's great. There is a reason for it. Single mode allows you to travel feet to 100 kilometers, give or take, and in some cases hundreds of kilometers if you throw in amplifiers. Multi-mode can't handle that. So why is that, right? So how does light work through a cable? It's fairly simple, right? You have a laser or an LED, and in this case, this is a single mode fiber. When we shoot a photon or a signal of light down the fiber, we call it single mode because that light only has one choice. It goes down that fiber in the direction it's shot, and it doesn't bounce around. And that's the key to fiber, right? If you shoot light in a straight direction, it will go very far. But if that light bounces around and moves a lot, it'll actually attenuate itself and not travel very far. So in a single mode fiber, we have specific manufacturing process, which again, we won't go into here, but this picture down here on the bottom right with the green on the sides represents what light does as it goes through that fiber. And when we show you the multi-mode, that'll make perfect sense. For those of us who test this fiber, you'll see at the bottom, which is the most important thing, what are the typical wavelengths? What's a typical light frequency we shove down this fiber. In most cases, we don't use the word frequency anymore in fiber. So if you come from a world of a wireless background and you're installing fiber now, you'll hear things like 700 megahertz, Wi-Fi, 2.5 gig, 5 gig, not 5G. When we talk light in a fiber, we tend to use length of the wavelength. So 1310 nanometers, 1550, 1625. Those are frequencies, but they're terahertz frequencies. So 1550 nanometers would be something like 196.43 terahertz, which means nothing to most of us on the phone, unless you're working very well into some higher end applications than we're selling our smaller tools for. So we deal with nanometers, right? Which is, how long of a meter is it? So 1310 is exactly what it sounds like. It's 1310 nanometers, right? And I'm sorry, a question just popped up, which, by the way, guys, I really like questions, so pop them in. Someone answered how you mute the microphone. We cannot hear you by default, so I believe you are muted. Andrew, Lindsay, correct me if I'm wrong there, just for whoever asked that question. So when we think about light through the fiber, this is the single mode version, right? Light goes down, goes in one direction. Now let's talk multi-mode. The reason it's called multi-mode is when you shoot that same photon of light through the fiber, not only does it go straight like the green line in the picture down below, which is the single mode version, but it bounces around. That core is so big, it's like an echo chamber, and light will bounce around. And as that happens, it will run into itself and it will actually attenuate itself. It will actually weaken the signal. Therefore, multiple modes of light, hence the word multi-mode fiber. Again, really good in short haul applications, really good in inter-office applications, very fast. You can still get your 100 gigs of data through it. You just can't go very far, which is why we don't tend to see it out in the outside plant world anymore. And we tend to use a shorter wavelength, 850 nanometers, which is a higher frequency, and 1300 nanometers, because we don't have to go as far, and they tend not to attenuate as much at these higher frequencies. So we're going to leave multi-mode alone. Everything else I do from this point forward is exactly the same between multi-mode and single mode. It's just a different of how the tools look at the tips, if you will. So this is just another graphical representation of multiple modes. You get basically hundreds of beams of lights going in virtually all directions, which is a huge problem for us. So what does that mean, right? How does fiber control light? And this is the beginning of how an OTDR works. So if we're following along with the agenda, this is the beginning of theory behind OTDR and fiber basics, right? So no matter what happens, whether you're single mode or multi-mode, when you shoot light down a fiber, the job of that fiber is to keep light in the core and deliver it from point A to point B. The way that does that is through a process of that glass tube and then a secondary glass tube around it. We call it cladding, which is like a mirror effect, right? It's designed to keep the light in. So what happens as your light goes through the fiber, it refracts or it bounces off of the inner fiber. And because of that, you can bend fiber. Because if you think of light in free space, it doesn't bend. We could talk about the sunset and all that later if we want to get into it, but light doesn't bend in free space. Shine a flashlight, it goes in the direction the flashlight's supposed to go. But fiber is pliable, right? It's bendable. That core fiber is not rigid, as we all know, because you guys have either rented or tested fiber, I'm hoping. And because of that outer cladding, you can bend it, and that cladding acts like a soft mirror, which allows the light to refract or bounce off of each surface in 360 degrees. Great, except when you bend too much. Right? So one of the number one principles when winning fiber is knowing what the minimum or maximum bend radius is before that refraction becomes a problem. I'm going to burn through this slide real fast. For those who like theory of how an OTDR works or light works, look up Rayleigh scattering and Fresnel reflections. Those two phenomena, if you like Wiki or just Googling it, check them out. This is exactly what's about to happen when light goes through. So let's talk about Fresnel reflections. And the reason to talk about it is this is the number one thing you're looking for when you use an OTDR. So as you transmit light down your fiber, what happens is that light goes through the fiber as we expect it to in whatever mode that happens to be in, and then it hits something. And that something is usually a connector, could be a splice, could be a really dirty fiber that's broken. But in most cases, let's just call it a connector for simplicity. So when light from fiber A hits the connector into fiber B, you will always have a small imperfection in the glass, which will cause a reflection of that light to come back down the fiber to the transmitting laser. And in our case, that would be an OTDR. So if you look at the picture, the drawing, excuse me, on the left, you kind of come down and then you see this massive spike right here. Let's see if I can draw a circle around that. I cannot. This does not let me draw like I thought it would, but that's okay. So we have the spike here. That would be a connector. Then we'd have another connector over here and some event here, whether that be a connector or something else. And that's what we look for, because there are metrics around these we have to pass in order to qualify this fiber to go on, right? So how does light work and how do we measure the distance of a fiber, right? One phenomenon that happens is light, whether that's through free space or outer space or fiber, it is a constant speed. I don't care if it's daylight or if it's in my case, very bright daylight in the picture behind me, or if it's a radio wave from your phone, or if it's a 1310 or 15 nanometer into your OTDR, into your fiber. They're constant speed. The speed of light is the speed of light. So we know that calculation. We know the speed of light in a vacuum, which we'll just call outer space right now, because there's no air and there's nothing to attenuate it. And then we look at the process from the manufacturer of the fiber, and we can calculate the speed of light through that fiber. And by knowing that phenomenon is why your OTDR can tell you how long a fiber is, just by shooting it from one direction, right? So I'm standing here and I want to shoot something, I don't know, 10 or 13 or 14 miles away. I don't have to have a unit on both sides. I just shoot it with the OTDR. And because of this principle we call index of refraction, in other words, the speed of light, excuse me, we can tell with fairly good accuracy how long that fiber is. And we can also tell you where your events are in that fiber. Again, your breaks, your bends, your splices, your connectors, all of that is done based on this principle right here. Again, if you like to Google stuff, index over refraction in an OTDR will really bore you with the definition, but this is effectively what it is. From a theory side, that's about as deep as I'm going to go because it's relatively simple. There's two phenomena, they're complicated, but the practicality of them is fairly simple, right? We look for events. I didn't really talk about Rayleigh scattering. We'll talk about that in a future slide in here, but that's the minute particles of light that reflect in the fiber itself, which is how we can tell the slope and some of the data between the events. That's all done automatically, no matter whose OTDR you're at, whether it's ours or my competitors. But now the important stuff. What is an OTDR really good at finding? It's really good at finding connectors. It's really good at finding splices because those are very obvious events that have happened. The fiber is going and something changes. Something changes, the OTDR can figure that out. And based on what change, we can figure out, is it a splice? Is it a good splice or a bad splice? Is it a connector, good or bad? Even types of connectors within reason. One of the hardest things for an OTDR to find is a bend in a fiber. So a typical bend in a fiber, like we're showing on this screen, is I've got this pliable piece of fiber here, and I don't know if you can see my video, but for those who can, as soon as I can get my unit out, you're going to see I have some fiber here in a knot, unfortunately. I can bend this, right? I can make it pliable. I can move it around. It's really hard to see with the black light there, the white background, sorry. But if I end up going too far, let's say I bend it to about here, light will go through, and that property of the refraction, the ability for that mirrored image to keep the light in the fiber will fail. We call that macro bending. So what happens? Light actually leaks out of the fiber. We don't see it because it's up at a frequency that is too high for us. It's out of the visible spectrum. Actually, Actually, it's too low. I apologize, I'm going the wrong direction. But it's in a light that's not in the visible spectrum, and yet it will attenuate the signal. So for any of you people out there that have done installation and you end up with too much fiber at let's say, a NID, let's not talk slack NIDs because they're there for a reason, but you end up with 10 feet, 15 feet of extra fiber in a cabinet. So what do? You take it, you put it in a figure 8, or you wrap it around itself and you zip tie it. And a lot of times what happens is that zip tie will kink this cable to the point where it will create a mini bend or a macro bend, and you will lose a ton of light through there. It's a massive problem, usually in the last 30 feet of the fiber when we're dealing with these fiber runs. And it's because there's just too much fiber. Or the inverse, not enough fiber. So what do? Pull a little bit, you try to stretch it. And glass bends, but it doesn't stretch. So then you pull it and you make a right angle right at the connector. Right? So you take something like this and you go, book, and you put a nice tight bend right there. We see that a lot in cabinets where they plug them into the device here and then they just let them fall. And that becomes a massive problem. That's a macro bend, and it causes a massive problem. The good news, all of those are fixable, unbended. Light is, the fiber itself is very pliable. It takes a lot to break fiber. And that's the bottom picture. Micro bending is broken fiber inside of the housing itself. When that happens, you replace the fiber right off the bat. You can't fix a micro bend or a shattering of the glass. And most people ask, how do you do it? Slam it in a cabinet door. Easiest way to break a fiber is accidentally have a little bit extra, shut the cabinet door, you click on the link, and sure enough, you've kinked that fiber. And that will 50% of the time cause a macro bend. And you're replacing that jumper, or you're cutting it off, and you're splicing on a new fiber in there. Which a lot of times, as you guys see this, you're going to have a nice long run of fiber to a junction box and an LGX panel, and then a short run. And that short run is there for a reason. It's a lot cheaper to replace short fiber. Most of the problems happen between the ends of the fiber on those edges of your network, not the stuff in the middle, because that's the stuff that's constantly being changed. So hopefully that makes sense. Stuff that we're doing in an OTDR. The good news, macro bending. Depending on the OTDR you use, if it's ours, and my competitors do this too, so I'll just say most of them, most of the higher end OTDRs will not just shoot a single wavelength to characterize your cable, but they'll shoot 2 wavelengths, like 1310 and 1550. So you guys who use OTDRs have seen that. The reason for both of those is twofold. One, connectors and splices act differently at different frequencies, and the network is evolving from 1310 to 1550, which we'll talk about with 2 slides here of why. And when you shoot those wavelengths, the macro bending can be calculated by the OTDR, and we can give you a pretty good accuracy saying that's not a splice, that's not a break, but you have a bend in your cable, and where is it? So then you can go there and go, whoop, and then shoot it again, and hopefully it works out. So that's the beauty of bending, is most of the good, better OTDRs on the market will do that. Not more expensive, but not these cheap little ones you can buy at Fred's Appliances or Fry's Electronics or something like that. But quality OTDRs between us and my competitors do it too. So let's talk about a couple things on connectors. All of us have probably seen connectors if we've worked with fiber. These are the most prevalent connectors in your network today, regardless of whoever's network you have. The prevailing one in a non-fiber to the home network is LC. Lucent connector, we call them Lima Charlies, little connectors. They're the small ones that will fit into something like an SFP. So you may have a small SFP here, something like this. This will fit 2 connectors, right? And it's half an inch, a little bit less than half an inch wide. They're the most common in all data centers right now, and we're using them in our 100 gig optics, and most client devices will use it. As you get into the core, we have the typical standard connector, Sam Charlie, a lot of people will call that. It's physically the same core, nothing changes. The only difference is it's twice as big as the Lucent connector or the LC connector. This is a standard for most communications that are not at the edge of your network, because they can be plugged into a machine once, or a router or a switch or an EDFA amplifier, and you don't touch them very often after that. versus the client side, these LCs, they're constantly being plugged in. And they take a lot of rack space, so they shrunk them down. The next two, the Frank Charlies and the Sam Toms, older connectors. We tend not to see those in newer networks now. These are BNC-like connectors for the RF people out there, the TDR people. They are push in, turn, right? They're not meant to be taken out very often. They're still viable in the network. We just tend not to see them as much on the newer applications. Then the bottom one. This is the MPO or MTP connector. The difference is the 4 above it, those are all single fiber connectors. 1 connector, 1 fiber. MPO, 1 connector, 12 to 24 fibers, all housed in that same the same size as the SC connector, 2.5, right? The 2.5 millimeter connector, second from the top. This is the new standard for data centers because again, I can get 12 connectors in, run that through a patch bay, and I only have 1 connector on each end to deal with instead of 24 connectors, right? So it takes your 24 connectors, brings it down to 2 connectors. Much harder to clean, much harder to keep clean because you got a ton of fiber in there you got to deal with. But once you get it, you're done. ×2, right? Per connector, and they go into breakout boxes, and you can do whatever you want there. Now, no matter which connector we're talking about, whether it's LC, SC, FC, Frank Charlie, or even MPO, there are 2 variants of that connector. There's I call it the blue and the green. I'm going to kind of ignore the multi-mode stuff at the bottom because that's not where we tend to spend a lot of time. But the blue is a ultra polished connector. So it's rounded like a baseball. So if you think of the end of the fiber, you've got this connector and it's polished equally on all sides. It works very great. It works very good in lower distance connectors. But because it is a flat connector, it causes some reflection issues. So they've come out with the angle polish connector, the green one. So what does the angle polish connector do? Instead of it rounded like a baseball, they cleave it off at an 8-degree angle. So it's like a knife blade, right? So you get your fiber up and then they slice it off at an 8-degree angle. That way, when you plug 2 greens in, the glass is not 90 degrees to each other. It's actually shifted off by 8 degrees in either direction. And that actually helps a lot, which I'll show you on the next slide, for how an OTDR works and how your network works. The only rule here, because one is rounded, the blue one, and the green is angled, you want to make sure you do not plug them in to each other on a regular basis, because that angled connector, as it's got a point on it, it will etch away and dig into that blue connector and eventually break the glass in there. It actually breaks the cladding on the outside of the glass first, but then that's, splinters like a windshield over time. So we advise not to do this. For those of you who have, there will be issues with reflections and loss. This is a very poor connector. Even if it doesn't physically hurt it, it's not a good connector because they don't made up perfectly. Right? And here's a drawing of how that works, right? So in an APC, you do this 8-degree angle here across the glass. So when the glass hits, it still makes a perfect connection, but there's that small angle. And what happens is when light hits the edge of the glass into the other glass, based on the phenomenon we call Fresnel reflection, the light's going to come back. Well, if you shine the light at an angle, it sure does bounce back, but it bounces back at an angle that pushes it outside of the fiber. That bending phenomenon we talked about earlier. So we don't want to see that in practice, but the tips do it based on their angle, which you do want that. So it allows the light to go forward, which is where it's supposed to go, and it minimizes all of the reflections coming back, which is bad. Reflections are very bad, which is why we don't want to see them in an OTDR. And so the analogy here is pretty simple. All right, take a flashlight, shine it out your window at night. If you shine directly at your window, you're going to see most of your light come right back into your face, and it's going to blind you. But take that same flashlight, tilt it out, let's just say 30 degrees for our example, and shine it out your window. You're going to be able to see the light hit the window. You'll see it bounce back and hit your wall somewhere else in your room, but you'll also see the light go through. That's the same phenomenon as an APC. It allows that back reflection, which is going to happen. It shoves it off somewhere else. Fiber to the home, fiber to the curb. A whole lot of cable companies moving to fiber have pretty much standardized on the green APC connector across the board. And a lot of that is still in the SAM Charlie or the SC interface, as you see in my picture here. The LC version of this, they exist. We don't see a lot of it yet, only because in PON or fiber to the home, you're not dealing with high data center rates. You're dealing with a small NID or a small, ONT box, and it will take that connector. So just a real quick hygiene on connector, or excuse me, properties of connectors. And then, types of cables, and this is more the do's and don'ts. Color for color is the way you want to match. That's kind of the rule of thumb. So you get an orange cable, you only want to plug that into another orange cable, regardless of the tip, right? The green versus blue, multi-mode tends to be gray. You get a yellow cable, you only want to plug that into another yellow cable. And then, of course, the tips, green to green, blue to blue. But what we find a lot of happens in older networks is you'll have these long home single mode cables, and then you get to the edge of the network and they ran out. So they'll take a multi-mode and plug it in. Now you're taking this tiny little light in a single mode and you shove it into a humongous core and it goes haywire, causes a lot of issues at the end. Can only work in maybe a couple meters to maybe tens of meters before it just attenuates itself out. So rule of thumb, color for color, with connectors and cables as well. Now, really the thing to remember when you think about qualifying your network, right? For those who worked on design of networks, you've got link budgets, and you've got power budgets, and you've got insertion loss budgets, all these things you work with, and there's calculators out there. If I were to take anything from this presentation, it would be this page right here as what do I need to know if I'm building a network or testing a network, right? And it's the absolute value of our case of doing decibels versus dBm, or decibels to a milliwatt, right? Everything you test in your network, if you're using just a power meter and some source, right? Whether it be this SFP as my source, the power meter is going to give me the raw power coming out of this, and that's great. Except it's going to give you the raw power after it goes through your network. So you still have no idea what the power is of this unless you're testing right at this. Or more importantly, if you don't know the output power of this, you read raw power, dBm power, absolute power, you're going to get a number. And that number is good because obviously you need to know what that number is at the end, but you're not going to know how well your network affected that number. Hence the dB, or the relative value, right? So a decibel value is not absolute. It's based on a known power source, like an OTDR, or a source, like a CW carrier tone source, and a unit on the other side that knows the output power. Or in an OTDR's case, it does the same thing with one box, right? So if I want to characterize my network, I want to test my fiber, I honestly don't care what the input power is or the output power, because that's the end devices. I care about how much loss is my network going to incur. So when Cisco shows up, for example, you can be certain that, yes, no matter what power you put through, I'm only going to lose 2 or 3 dB through there, and it's going to come out the other way, right? So this is a really good slide and a couple cheat sheets for those of you who may not know how a decibel works. The rule of 3 is the best way to do it. If you see the number 3, whether it's plus or minus on an insertion loss measurement, which you will get on your OTDR and from us and other people, you've lost, or in this case, if I have plus 3 dB, I've actually doubled my power. So from a car amplifier, if I had a 100-watt amplifier and I had a knob that said plus 3, I would change my 100-watt amplifier to 200 watts by just moving that 3 dB. More importantly, for us, is the negative number. If that's negative 3 dB, I've lost half my power. That's a bad number, right? You don't want to lose 50% of your power through anything, right? And what happens is your connectors, your splices, your fiber itself, your bends highly affect this number, right? And then the other rule is 10, right? If I see a 10, I've lost 10 times the amount of power, right? I went from 100 watts to 10 watts based on that number. So it's not linear like we're used to doing. It's logarithmic. So these small numbers have drastic changes. And understanding this type of information in your process of looking at any test and measurement item, right, is huge, right? You can tell these little minute changes that look like nothing cause drastic problems in network. Right? So how do we stop that? What's the best thing we do in the next 15 minutes, right? We deal with the connectors. OTDRs are great. You're going to get them from your customers. You're going to have to shoot them. You're going to have to produce a report. That's just the way that half of these service providers want to work today. And the reason for that is you're going to have minimum two connectors, one on each end, 2, 15, 10, 5, 30. You never know. It all depends on how long the network is and how old the network is, because nobody replaces the fiber. They splice it and they add new fiber to it. But core fiber underground tends to stay underground for 50 years, give or take. So if I can measure the fiber, but there's nothing I can do about it, I have to quantify that out. So what's left in a fiber network that we have to deal with from an installation, maintenance, and ultimately a tested measurement issue that we have, right? Where do we come in? The connectors, period, right? At the end of the day, 80% of your problems that you can remedy are your connectors. And I do mean splices in that too as well, by the way, but we're going to focus on the easy stuff because splices are, hey, I got something bad, I got to roll up a fusion splicer and put it back together, right? And then you just test it. But connectors, right? Connectors are the #1 point of failure. Again, roughly 80%. So how does a connector work? This picture here is 2 connectors. We'll call them LCs because that's what I'm used to dealing with a mating sleeve in the middle, or a bulkhead adapter, or an LGX panel. They're all the same. Piece of plastic with some areas for these things to clamp into. And then a sleeve right here, which is open. And so what happens is when you plug in your connector, no matter which type of fiber, there's a backstop here in blue on the screen that pushes the protection of the core backwards, allows the fiber and the cladding to be exposed, also some of the plastic on both ends, and then this sleeve is just an alignment sleeve, and they connect together. So what does that look like? Looks like that. Seems simple. It is simple. And these connectors are, these little bulkhead adapters are really, really cheap. I don't have one to show you here. I thought I did. Actually, I do. So these type of connectors right there, right? This is a 4-port bulkhead adapter. If you can find my camera. These are cheap. They're just little plastic guys, right? With a little sleeve in it. You can kind of see through it. Well, maybe you can't in the video. That connector is brutally vital to your entire network. That physical contact through these cheap plastic things is what will give you a working network versus non-working network. Maybe not one connector, but there's never just one connector in a fiber plant, right? There's going to be, let's just imagine there's 10. Let's just use a round number. In almost every plant, you're going to have a roughly 10-ish connectors. You get 2 or 3 of these going bad, and it takes down an entire network, right? Some guy kicks a cable on the floor as you're walking by, and it will rip these things apart so fast, right? So that's what we're going to focus on for the next couple sections here. So how do we verify? How do we guarantee to the best of our ability that this connector here is going to go over to this? Oops, there's animation here. Sorry about that. To this connector here and not cause a problem. And this is what I call the most intuitive slide ever. If there's any impurities between connector A and connector B here, you're going to have an air gap, and that air gap is going to cause attenuation. It's going to cause the light not to go through, and it's going to cause a reflection for the light to come back. And both of those are roughly equally as important, right? Going to pause for 1 second. William asked a question. Is there a significant difference between ceramic and zirconia? I still cannot say zirconia. Sleeves and a bulkhead. I think from a practical standpoint, no, there's no difference in the job that they do. They're adapters, right? The difference becomes which ones are more durable over time. Bulkhead adapters are built to plug in and unplug and plug in and unplug. More expensive ones tend to have better quality parts, whether they're ceramic or not. I honestly don't know the answer to that one, but higher quality connectors like an LGX panel versus the cheap little blue ones I buy off the web, they're going to be higher quality, therefore higher price, therefore they're going to handle the constant plugging in and plugging longer. That's really what it comes down to. And it's the manufacturing process. Buy some cheap ones, you get cheap ones. Right? It's kind of rules of thumb. Right? So hopefully that helps answer the question. Okay, so back to this slide, right? Dirty fiber. And there's a lot that creates dirty fiber, right? But basically, any impurity on the fiber face will cause an air gap between fiber A and fiber B. That air gap will cause problems. The amount of problems depends on the dirt, depends on the connector, depends on what happens at the tip. And I'm not talking again about bending or broken fiber or all of that fun stuff. That's where the OTDR comes in. But here's the ramifications of what happens between a dirty and a good connector in a really, really old OTDR trace. Connector 1 is, through a microscope, is pristine. Here's my single mode core. Hopefully you guys can see my mouse. The core is the white part of the picture number 1. The dark gray is the cladding. That's that mirrored interface I talked about before. Its whole job is to keep that light in that center core right there. And then the gray is just plastic, and it could be ceramic for the actual tip itself. Again, that's protection to keep everything in that light. In the picture on the right, you have an event here, number 1, and an event here, number 2. Normal events, you're always going to have some sort of back reflection when you plug into connectors, because we can't, without a fusion splicer, without fusing the glass together, there's an event. And these guys lost 1/4 of a dB, give or take, right? 0.25, 0.24, totally normal. Then you take a dirty one, like this one, which has just crud on it, right? A lot of crud around the outside, a lot of crud in the cladding, most importantly, crud in the actual light itself, the core. That's connector number 3. So what this tells me is connector number 3, in an OTDR's case, came back with I got a loss of almost 5 dB here versus 0.2, right? This is an extreme example. Yours will be probably more in the 1 to 2 dB range. But again, at 3 dB, I've lost 50% of my power. I'm at 5 dB, so I'm up about 70 or 80% of the power just dropped instantly because I have a dirty connector. And if you're an OTDR fan, that's the drop between this green line where my mouse is and this green line. That one connector was so bad, it drops the power instantly, which is what happens on the far end. Not to mention the back reflections, which that's a little more detailed, but back reflections are exactly like I talked about the flashlight in the window. They blind the laser. So if you're using a laser that is sensitive to light, it will actually blind it to the point where it'll burn itself out and actually kill it. But that's more complicated. It takes a lot to do that. We're going to not really focus on that. So let's just take an example of what does this look like, right? So you have dirt on a fiber, and the pictures on the left are real, picture on the right, obviously not real. So you've got these dirt particles. If you don't inspect and clean, which is, by the way, for the cheat sheet, that's where I'm going with all this, and you plug it in, first time you plug it in, it's going to do one of two things. If particles are big enough, it's going to shatter them. It's going to break them, right? And create more dirt. If they're small enough, it's going to embed them in the glass. Since this glass is bendable and pliable, it's also soft relative. So it's going to embed them in, creating permanent damage. You plug it in another time, it's going to move them around if they're the big ones, and break them again and embed them again, and so on and so on. So this is the reason dirt is a huge problem. For those who've worked in the field, sorry, excuse me about that. For those who worked in the field, it's a dirty environment. You know, I don't care if you're 400 feet up a pole or in a data center or in underground in these junction boxes, right? Dirt's everywhere. And you have to remember that little piece of light that was in there, that core, is smaller than a human hair. So the amount of dirt it takes to actually block light is infinitesimally small. So we like to show these pictures. I call them the fear slides because they're scary, but all of this is realistic. Right? First is copper. If you come from a copper background, man, you could dip copper in the mud. Who cares? It's just copper on copper contact. Plug it in and have a good time, right? As long as you don't cross thread units, or I don't know why I can't think about what that's called today. We'll call it cross-threading. I think that's it. It didn't matter. You just needed contact. In fiber, you need contact, but you need clean contact, right? So a couple examples of what is clean versus dirty in a microscope. Top one, you want it to be as clean as possible. That's great. dirt, which is all of our last examples. Pretty simple. I'm going to skip oil for 1 second and go to pits and chips. It's what happens after dirt's not cleaned and you plug it in a couple times. And then, of course, scratches is when dirt does move across the lens as you're plugging and unplugging. People tend to shake a little bit and it, scratches it like sandpaper. Dirt's cleanable. Bits and chips and scratches are not cleanable. Eventually, you just cleave it and fusion splice an end on, or replace the jumper if you're doing with short jumpers. Oil, on the other hand, is interesting because it's oil. So where does it come from? Honestly, it comes from your thumb usually. So you grab your connector and you accidentally rub your thumb across it, or you scratch something if you really don't know how to take care of fiber. But body oil is what gets on the tip of the fiber. And it happens more often than not, is you go through the process, you've inspected, you've cleaned, you're holding it in your hand, and somehow your thumb gets too close to it and the oil on your skin pops into it. Super cleanable, as long as you know you did it before you plug it in. And that's a little bit, not as black and white as don't plug it in, but when you do see oil in a microscope, it will look like this, right? This is just blobs of oil. And again, these are really small, so it's not that much. Doesn't hurt anything until you plug it in, right? When you plug it in, since oil is a liquid, what's it going to do? Well, it can't compress because water doesn't compress, so it moves. When you plug two fibers together, you end up seeing this ring around it, which is the contact zone of the other fiber and all of that plastic, right? And you'll see the oil moved out to the areas I don't care about, and it moved into the areas I do care about. So it's a easy phenomena as you go and see other people's work or your own work and you're inspecting it. If you see oil with this clean patch, it means somebody plugged it in after getting oil on the lens. And then here's the bad news about oil. As light goes through the fiber in the working network, it creates heat. The heat takes that oil and it melts off or evaporates. It's melts off, not the right word. It evaporates the liquid and it leaves the grime of oil in there, which then embeds itself into the glass. We call it the coffee ring because it looks an awful lot like a coffee ring around it, and there's no way to clean it because it embeds itself in. The important part of this slide isn't so much the ring on the outside, it's the spots that have burned themselves in on the inside. If there are enough impurities in there, they work like dirt and they create gaps, they create reflections, they're non-cleanable. But the tell sign is that ring around the side, right? For those who've played with fiber, you've seen it most likely. If not, just rub your thumb across it and go look at it with a microscope. And then, you can amaze your friends at parties with how gross your skin really is. And not anyone in particular, just in general. So here's the good news. When you do scope through my scope, my competitor scopes, most scopes on the market, we all test to a criteria. It's the IEC 61300 or 61300 criteria. I don't care if you know that. What I care is there is a standard for what is a clean versus a dirty fiber. For those who've been doing this for a while, analog scopes, you'd get in there and you'd scope it and you'd eyeball it. That works really good about 60 to 70% of the time. But what happens is you miss scratches and you miss these small things that may have affected the core, and digital scopes that can test to our criteria will pass them or fail them based on the criteria you see on your screen, right? What's also good, which I like about this, is you're gonna pass fiber that has dirt on it. There are times when you're gonna see imperfections in this fiber, you're gonna see dirt, and it's gonna pass, and you're gonna go, it's not clean. That's okay. If it's in zone D, which is the it's the contact zone, it doesn't really matter as long as it doesn't create a massive gap, right? So if you look at their criteria, that's got to be 10 microns, which is pretty big, right? But you go closer and closer to the core, and they start getting smaller and smaller, because the closer you get to that core, the worse your fiber, the worse your connector is going to get. So cleaning kits, I don't sell them, which is good. So we just pulled one off the web. Plus these guys gave us a bunch of free samples. So, we're doing them a favor by putting them up there. Stickler makes them, TRS-RenTelco. I know you guys supply these. If you're not doing Stickler, I should probably know that so I can take these out next time. Typical cleaning kits, cleatops. I love cleatops for fiber ends because they tend to be really good at keeping the dust off the surface of the cleatop. A lot of them have this little door and click on it. but they only clean half the fiber, which we'll talk about in a minute. And then of course 1 clicks, or as I call them, 7 clicks. These are really good at cleaning if the dirt's easily accessible, right? It's not been embedded. Then past that, you've got swabs and wet cleans and all the other fun stuff you guys know, right? For those who've been doing this. So how do you scope it, right? What is inspect before you connect? This is our phrase, right? Pretty simple. If you pull the fiber out of a connector, do you clean it first or do you inspect it first? Most of us carry 1 clicks. Most of us like to clean it first, and I'm absolutely guilty of that because it takes time to inspect. But these 1 clicks and clean up to a point, they hold dirt too. They're lint-free cloth is what they are effectively. Dirt can get in there, and you can actually put dirt right back into a perfectly clean connector. So best practices, a scope. Again, it doesn't have to be one of ours, but obviously we're hosting this with TRS. We want it to be one of ours. And these are all digital scopes now. They will test to the standard. And then depending on the tip, you're going to test the tip itself, but you're also going to check what the tip is plugged into. Because these bulkhead adapters, these LGX panels, it's nothing more than, again, that pass-through with the fiber on the backside. And everything we talk about on these fiber tips is exactly the same as the fiber on the backside. So you need to inspect both and technically clean both, right? And I won't bore you with the propaganda slide. If you get a copy of this, you'll see it. But this is how the slide works, right? You have a focus tool. Depending on your fiber type, you have a tip, and you have a go button, and there's some software that displays the results and allows you to print reports and baseline it for your customer, right? We also do, in our case, the fiber check probe, which takes, I'm going to go back a slide, takes the software out relative. This unit is USB to a test set or an Android phone or a PC. I already said test set for us. It's great, but you need a device, right? This unit is self-contained. It's got a battery, it's got a flash drive, it's got an onboard little Raspberry Pi, I guess, I don't really know. But you pull the trigger, it will autofocus, and it will give you your results right on the screen. So you'll know if you passed or failed. You don't have to carry anything other than a battery charger because it takes a USB battery charger like everything else. Still works with the PC, still works with all the instruments. You just don't need them, right? And it'll restore and record and all that fun stuff. So tips, right? The next thing when you're inspecting isn't just inspecting because every fiber is slightly different. So we have SC blue or the UPC. You've got 2 tips. You've got the tip for the fiber. You've also got a tip for the bulkhead, which is for the fiber on the other side, right? If you're an APC, you've got a tip for the bulkhead, you got a tip for the fiber. If you're an LC, you got a tip for the bulkhead, you got a tip for the fiber. And we like to do these long reach tips because sometimes your batch panels are back, but they're the same thing, right? You need tips, TRS has tips. Our catalog is some 200 plus tips, depending on your fiber application. So in most cases, these are good enough, but you'll see. Now, my trick for doing this, I don't like these tips. Not that they're bad tips, but in dealing with fiber, you're dealing with an extremely small little cladding thing right there, right? The little white part, if you guys can see my video, which is fragile. And if you're like me, you slip and you break it. So what we've developed, and I'm going to go back here, instead of doing this, which everyone does, we didn't develop it, we just kind of figured it out through best practices. Instead of using this tip and constantly getting this dirty and then swapping to this tip, the bulkhead tip over here, why not carry these, $2 bulkhead adapters like I have, use the same tip, and then take your bare fiber, not bare fiber, your terminated fiber, plug it into the backside, and if it's duplex, plug both sides in, and now you can use the same tip on your probe to test not only the fiber, but also the bulkhead, and you're not unscrewing it, putting in the new tip, screwing it, moving back around. It will save you time. It protects this unit also. So the fiber tip is inside the little bulkhead. So if you do drop it, it's got a little bit of protection. It also keeps the oil from your hands off of it. There's a lot of reasons to do this. And again, I don't sell these, but they're great. Amazon or I use fs.com. That's my favorite place to go right now. But any of the suppliers will have these, right? It works very well for both LC. And then the next kind of tip is if you're dealing in an environment where you're dealing with LC and SE, they do make these adapters. Not loving these adapters in the real world because they tend not to line up perfectly. But from a scope point of view, if I'm an LC guy, but every once in a while I have SE, I can plug an SE in here and use my LC bulkhead tip. Or vice versa. If I'm an SC guy and I have every once in a while an LC, I can reverse this picture and not have to move my tips around. These little guys are great. I absolutely recommend having them in your arsenal. They're brilliant for helping you guys speed up your testing. And the same is true for the infamous one-click. I lose this little cap off my one-click usually within a day or two because you've got it in your pouch and you pull, and well, I like to pull on that tip. And if I put it in upside down or tip down, it gets caught on something and I break it off. Use that same bulkhead adapter as a cleaning adapter. So you now can use your one-click for both. I don't recommend replacing your cleat top, but it allows you to go through there, right? And I'm only got 2 slides left and we'll wrap it up. Our software, if you do have ours, by all means, download it on that site, Update My Unit. It's free, runs in a PC. There's also a software for your Android phone and your Apple phone, but understand Apple phones don't work with USB, so be careful on that. They do work with the new Pro. And this is the final slide for me, and then I'm going to hand it over to Michael. If you have the Android device, everything we talk about allows you to see it, record it, and look at it on the Android device. And again, Apple, if you're using a probe like this that has Wi-Fi, 100% Apple, and of course PC as well. So with that, I'm going to hand it over back to Michael and say thank you to everyone for listening to me drone on.
Well, thank you, Dan, and thanks, Dan, for having done a great job today in this session. I hope everyone found the webinar to be extremely informative. If anything, it looks like cleanliness, Dan, definitely is next to godliness.
My wife would agree with you. Yes. My kids would not.
I would like to remind everyone also that if you are looking to acquire any of the Viavi test equipment mentioned throughout this presentation, please reach out to us at the following email address at the top right-hand corner of the slide, sales@TRS-RenTelco.com, or by calling our toll-free number at 1-800-874-7123. Our application engineers are actually standing by to provide you with cost-effective solutions ranging from flexible term full service rentals to operating and capital leases, as well as 0% financing for our certified pre-owned equipment. So if there are no further questions, this would conclude our webinar for today. Any questions?
I believe we need to type those in the chat window. Is that correct?
Yeah, doesn't look like there's, I don't see any, Dan, do you?
I only see one question. That's from Brian. I'm impressed you saw that. Most people don't know what that is. So good for you, Brian. It's awesome.
That's great. So if there are no further questions, this will conclude our webinar for today. I would like to thank you all for your participation, and we look forward to working with you soon. Thank you, everyone. Thank you, Dan.
No problem. You guys have a good day.